All right, so now that we better understand what this quantifier most means, and as a reminder, most also speaks of a range, just like sum, right? But the range for most is smaller. Specifically, the floor is raised, right? The lower bound for most has to be more than half. Here in this lesson, I want to focus on translating most to logic. And the rationale is the same, right? Logic gives us a clearer way to evaluate validity and hence to help us identify reasoning errors. To get on with translation, we first have to learn the element in logic that represents most, and it's this most arrow. Okay, it's this most arrow here. Now, the first thing I want you to notice is to contrast this most arrow with the sum arrow. Notice how the most arrow is unidirectional. It is a one-way street, just like your standard conditional arrows. It does not point in both directions. That's different from the sum arrow, which is a bidirectional arrow. It points in both directions. Remember, we said in the sum lessons, you can read some claims in either direction. If some cats are pets, then yeah, some pets are cats. Those are the same claim. Those two are saying the same thing. This is not true with most statements, right? That's one of the reasons why the arrow points in one direction only. It's because you must read it unidirectionally. You cannot read it reversibly. So let's practice translating a most claim from English into logic. Again, it's going to be this claim here: most students in Mrs. Stoops' class can read. First step, identify that this is a claim in English that is amenable to translation into logic. And to do that, we identified the indicator or quantifier, right? The word most. Next step, we identify the two main concepts or sets, right? Typically, when we're dealing with quantifiers, unlike conditional logic, sets is usually what we're dealing with, right? So here, one set is the set of students in Mrs. Stoops' class. The other set is the set of students or people who can read. The next step is to assign symbols to represent those two sets. And I'll just use the same symbols as we used in the sum translation, right? Student for students in Mrs. Stoops' class and read for students or people who can read. And then the final step is just to add in the most arrow. In logic, this claim says students, most arrow, read. Now, again, I want to emphasize that the arrow is unidirectional. Okay, this is the point of difference between the most arrow and the sum arrow. You cannot read this the other way around. If we mistook this claim for the claim that read most arrow student, that would be a very bad mistake. This is in fact one of the most reliable traps that you will encounter on the LSAT. These two claims are simply different claims. They're not identical claims. In English, this claim says that most students that can read are in Mrs. Stoops' class. That's kind of crazy, right? Whereas the original claim is just, it's just a normal claim. Most students in Mrs. Stoops' class can read. Okay, so, she's got some pretty clever students or she's a great teacher, right? Nothing weird about that. Whereas this claim, most students that can read are in Mrs. Stoops' class. I mean, how large is her class? She's teaching what, millions of students, right? Visualized, the difference is that whereas the first claim is pushing the set of students in Mrs. Stoops' class into this other set called students who can read, and it's doing this pushing in a way that at least half of this set has to go in here, right? That's how we can satisfy most students in her class can read, right? That's what this first statement is doing. Again, just like a fairly normal claim. This second claim is doing something crazy. The second claim is saying, of all the students in this set, we have to push most of you into here. Well, I mean, I can't. This set is too small. If I want to make the second statement true, I first have to make Mrs. Stoops' class humongous in order just to accommodate this move that we're about to make, right? Which is that, of the entire set of students who can read, I have to push most of you into Mrs. Stoops' class. So you see what I mean? They're just different claims. And if you confuse one for the other, well, chances are there's going to be a trap answer choice waiting for you. So maybe another way you want to think about this is the distinction between the claim that most dogs are pets, right, which would translate into logic D, most arrow P, versus most pets are dogs, which translates into P, most arrow D. I mean, again, these two are not the same claim, okay? Not at all. They are incredibly different claims. The first claim is probably true, right? If I think about all the dogs, the entire set of dogs, yeah, probably most of them get pushed into this, other set called pets, right? I would even say probably like the overwhelming majority of dogs are pets. I mean, at least in this country. But whereas this other claim, most pets are dogs, come on now. There's so many other kinds of pets, right? They're cats, they're rabbits, they're hamsters, fish, reptile, the list goes on and on and on. It is just not true that most pets are dogs. Okay, and again, if we wanted to make this claim true, the first thing you have to do is you have to increase the set. You have to say there's so many dogs, right, that it can accommodate most of this other set called pets. Okay, so let's review. To translate most claims to logic, use the unidirectional most arrow. The arrow is unidirectional because the most intersection relationship does not work both ways. Most A or B is not identical to most B or A.